General material classifications. There are thousands of materials available for use in engineering applications. Most materials fall into one of the three classes that are based on the atomic bonding forces of a particular material. These three classifications are metallic, ceramic, and polymeric. Additionally, there are different materials that can be combined to create a composite material. Within each of these classifications, materials are often further organized into groups based on their chemical composition or certain physical or mechanical properties. Composite materials are often grouped by the types of materials that are combined or the ways the materials are arranged together. A list of some of the commonly classification of materials within these four general groups of materials. Metals. Under metals, ferrous metals and alloys, which are irons, carbon steels, alloy steels, stainless steels, tool and die steels. Remember, ferrous comes from the Latin ferrum, meaning iron. Ferrous metals contain iron. Non-ferrous metals do not. And the non-ferrous metals and alloys are aluminum, copper, magnesium, nickel, titanium, precious metals, refractory metals, and superalloys. Polymeric. Polymeric materials. Thermoplastic plastics. Thermoset plastics. And we will define the difference between these two materials further on in the presentation. Elastomers. Ceramics. Glasses. Glass ceramics. Graphite. Diamond. Composites. Reinforced plastics. Metal matrix composites. Ceramic matrix composites. We have sandwich structures and concrete. Each of these general groups will be discussed in more detail in the following slides. We will look at these manufacturing materials and engineering materials by starting with ceramics. Ceramics have traditionally been defined as an inorganic, non-metallic solid that is prepared from powdered materials, is fabricated into products through the application of heat, and displays such characteristic properties as hardness, strength, low electrical conductivity, and brittleness. The word ceramic comes from the Greek word keramikos, which means pottery. They are typically crystalline in nature and are compounds formed between metallic and non-metallic elements, such as aluminum and oxygen, which is alumina, calcium and oxygen, which is calcia, and silicon and nitrogen, which is silicon nitride. Depending on their method of formation, ceramics can be dense or lightweight. Typically, they will demonstrate excellent strength and hardness properties. However, they are often brittle in nature. Ceramics can also be found to serve as electrical conductive materials or insulators. Some ceramics, like superconductors, also display magnetic properties. They are also more resistant to high temperatures and harsh environments than metals or polymers. Due to ceramics materials' wide range of properties, they are used for a multitude of applications. The broad categories or segments that make up the ceramic industry can be classified as structural clay products, such as brick, sewer pipe, roofing and wall tile, flue linings, and materials such as that. Whitewares, which are dinnerware, floor and wall tile, electrical porcelain, and etc. Refractories, brick and monolithic products used in metal, glass, cements, ceramics, energy conversion, petroleum, and chemical industries. Glass, flat glass, such as windows, container glass, such as bottles, pressed and blown glass, such as dinnerware, glass fibers that's used in home insulation, and advanced specialty glass, such as optical fibers. Abrasives. Abrasives can be natural, such as garnet, diamond, and synthetic, such as silicon carbide, synthetic diamond, fused alumina, etc. Abrasives are used for grinding, cutting, polishing, lapping, or pressure blasting of materials. Grinding wheels in the machine shop are ceramic, or considered ceramic. Cements. Yes, cements are also considered ceramic and fall under that classification. Cement for roads, bridges, buildings, dams. We also have an advanced ceramics category, such as structural, which are wear parts, bioceramics that go into making new knees, new hip joints, cutting tools, and engine components. Electrical ceramics, such as capacitors, insulators, substrates, integrated circuit packages, piezoelectrics, magnets, and superconductors. Ceramic coatings that are used in engine components, cutting tools, and industrial wear parts. Chemical and environmental ceramics that are used in filters, membranes, catalysts, and catalyst supports. The atoms in ceramic materials are held together by a chemical bond, which will be discussed a little later in the presentation. Briefly though, the two most common chemical bonds for ceramic materials are covalent and ionic. Covalent and ionic bonds are much stronger than in metallic bonds, and, generally speaking, this is why ceramics are brittle and metals are ductile. Next, we're going to talk about composites. Now, composites cover a wide range of engineering materials. We could spend a whole semester talking about all the composites out there, but we're just going to go over a few of them. A polymeric solid can be thought of as a material that contains many chemically bonded parts or units, which themselves are bonded together to form a solid. The word polymer literally means many mers, or many parts. Two industrial important polymeric materials are plastics and elastomers. Plastics are a large and varied group of synthetic materials which are processed by forming or molding into shape. Just as there are many types of metals, such as aluminum and copper and steels, there are many types of plastics, such as polyethylene and nylon. Elastomers, or rubbers, can be elastically deformed a large amount when force is applied to them, and then can return to their original shape, or almost, when the force is released. Polymers have many properties that make them attractive to use in certain conditions. Polymers are less dense than metals or ceramics. They resist atmospheric and other forms of corrosion, offer good compatibility with human tissue, or exhibit excellent resistance to the conduction of electrical current. The polymer plastics can be divided into two classes, thermoplastics and thermosetting plastics, depending on how they are structurally and chemically bonded. Thermoplastic polymers comprise of the four most importantly commodity materials: polyethylene, polypropylene, polystyrene, and polyvinyl chloride. There are also a number of specialized engineering polymers. The term thermoplastic indicates that these materials melt on heating and may be processed by a variety of molding and extrusion techniques. Alternately, thermosetting polymers cannot be melted or remelted. Thermosetting polymers include alkyds, amino and phenolic resins, epoxies, polyurethanes, and unsaturated polyesters. Rubber is a natural occurring polymer. However, most polymers are created by engineering the combination of hydrogen and carbon atoms and the arrangement of the chains they form. The polymer molecule is a long chain of covalent bonded atoms, and secondary bonds that hold groups of polymer chains together to form the polymeric material. Polymers are primarily produced from petroleum or natural gas raw products, but the use of organic substances is growing. The supermaterial known as Kevlar is a man-made polymer. Kevlar is used in bulletproof vests, strong lightweight frames, and underwater cables that are 20 times stronger than steel. And again, on this slide, you see some examples of thermoplastic and thermosetting polymers. And remember, plastics can not only be machined, but you can weld plastics also.